Today's daily code problem of the day is minimum obstacle removal to reach corner number 2290. For this problem, we're given a zero index 2D integer array called grid, and it's going to be a size m by n. Each cell is going to have one of two values: a 0 representing its empty cells, a 1 representing an obstacle that may be removed, and we can move either up, down, left, or right to any of the empty cells. We want to return the minimum number of obstacles to remove, so you can move from the upper left corner to the bottom right corner, or m-1, n-1. So, how are we going to approach this problem? So, for this problem, we are going to start in this top left square, in the pink X. Our goal is to reach the blue X, right? So, what is the cheapest / fastest path to get there? Because of the nature of this problem, we are going to approach it like a graph with weighted edges. So, what does it mean to have a weighted edge? A weighted edge is basically going to be a node that costs money or some form of currency to move to, and we want to minimize the currency that we have to spend. So if we have to move to an obstacle node like this one, that's going to cost us 1. If we have to move to this obstacle node, it's going to cost us 1. And that's going to eventually add up. And our goal is to add up and see what the total cost is for us to get from here to here. So there's multiple paths we could take, of course. We could go this path I drew. We could go here. We could go here. You know, there's an endless amount of paths you could take to reach the blue X. Our goal is, again, to find the cheapest path, and there's multiple cheapest paths, so we're going to have to keep that in mind. There's this path, there's this path, there's this path, which are all going to charge us 2 units because we had to go through 2 obstacles to get there. So, how are we going to approach this problem? Here's another example. Example 2, we're going to start here. Our goal is to get here. For this problem, we don't have to spend a single node of currency because we can simply avoid the obstacles. So how are we going to do this? We're going to use something called the Dijkstra's algorithm. I'll get to that in a second. Let's go ahead and just go over the approach from beginning to start. This problem boils down to finding the shortest path in a weighted grid. So here's our plan. We're going to use a priority queue or a minimum heap to process cells with the fewest obstacle removed first. Meaning, in something like example 2, we're going to look and see that we can either move right. We can either move right and run into an obstacle, or move down and run into no obstacles. So we're going to move down first. And then we can see, same thing, either right or down. We'll go down first. We're going to track the minimum obstacles, maintaining a minimum obstacle grid to show and store the minimum number of obstacles removed to reach each cell. So to reach this cell, we don't have to remove any. This cell, we don't have to remove any. Same. In this case, for us to reach this cell even, you're going to have to remove some nodes, and we will keep track of that in our minimum obstacle grid. We're then going to explore the neighbor of each cell in all 4 directions, up, down, left, right, in search of a new path. If a new path removes fewer obstacles than are previously known, we'll update the value and continue the search. So this is a variation of the Dijkstra's algorithm, where the weight of each cell is determined whether it's an obstacle within 1 or not with a 0. So, what exactly is Dijkstra's algorithm? Dijkstra's algorithm is one of the most popular algorithms for finding a shortest path in a graph. It works for graphs with non-negative edge weights and is commonly used in navigation systems, network rerouting, and other optimized problems. Here's how it works. We're going to start with a source code, meaning we're going to, being from a starting point, like the top left corner of our grid, up here, we're going to track the shortest distance. We're going to maintain a record of the shortest distance to each node and use priority queue or a minimum heap and the node with the smallest distance will always get processed next. We will then repeat this algorithm, continuing until all nodes are processed or until we reach our target node, like our bottom right node in our corner of our grid. And the Dijkstra algorithm always ensures that you always process the optimal path first, which means it's very efficient for problems like this. Where it fits in our problem, the weights of our graph are defined by whether a grid cell is an obstacle with a 1 or empty with a 0. We're moving through an empty cell with a 0 has no cost. Moving through an obstacle with a 1 has a cost of 1. By using our Dijkstra algorithm, we efficiently find the path from the top left corner to the bottom right corner with the minimum number of obstacles needing to be removed. So let's go ahead and jump into the code for this problem. Well, the first thing we're going to do is identify a public to this class. So a private final integer grid, and this is going to be our directions. These are going to be the 4 directions that we can traverse our grid in. So that means we can either not move our x and move our y. We can't, oopsies. And then we can not move our x, but move our y down. And then we can move our x, but not move our y. And then we can move our x down, or to the left, and not move our y. And those are our 4 possible directions that we want to keep track of for our traversal. Next thing we're going to do is initiate all of our cells. Sorry, we're going to first get our grid lengths and then set up our grid minimum obstacles to keep track of everything. So int m is going to be equal to our grid dot length, and n is going to be equal to grid of 0 dot length. These are just the previously given variables. And then we have our integer 2D array called min obstacle, which is going to be keeping track of the minimum amount of obstacles needed to reach each cell. Then we're going to initialize all the cells with a very large value, because if they have a very large value, this essentially means to us that these cells have not been visited. So we're going to have a nested loop to traverse the entire grid. So for each integer I, 0, as long as I is less than our m value, I can increment. And for each integer j is equal to 0, as long as j is less than n, j can increment. And we're simply going to set min obstacle of I of j equal to integer dot max value, which is pretty much as close to infinity as you can get, and that will simply represent an unvisited cell. Next thing we're going to do is start from our top left corner of our grid and account for its obstacle value, and then we're going to traverse the rest of our grid. So min obstacle of 0, 0 is going to be equal to grid of 0 of 0, which I'm assuming is going to start at 0. They do not give us a clear answer whether the starting position is going to be 0 or 1. So we're going to equal it to grid of 0, 0, just in the case that it could be an obstacle. Next thing we're going to do is set up our priority queue. And it is going to be of integer arrays. Jeez, what is going on with priority queue of integer arrays? And we could call it our PQ, which is a new priority queue. Now, when you're defining a priority queue, you also have to define how things are sorted. Because it's a priority queue, it's going to automatically sort the smallest at the top. We want it to be kind of, we want the greatest at the top. So we're going to have A and B. These are going to be 2 values, value A in the priority queue, value B in the priority queue. And this is our lambda function. We are going to compare A and B by checking A of 0 and subtracting that from B of 0. So if A of 0 is greater than B of 0, it will be on top. Then we're going to starting at the cell that we're currently at, we're going to add it to the priority queue. So pq.add new integer array, because that's what's being stored in our pq, and it's going to be min obstacle of 0 of 0, and then we're also going to pass it 2 more zeros. So this is basically representing, this is minimum obstacle 0 0. That's the value at grid of 0 0, and then this is 0 and 0 representing the row and the column of the index. We're doing this to keep track of the position of each cell as well as the value of what it is in that cell. Because let's say we add this to the queue and we want to pop it out, this value is either going to be a 1 or a 0. This is not going to be minimum obstacle of 0 0. It is going to be either a 1 or a 0. And to keep track of the position of the cell, we are going to use 2 more variables, the x-coordinate and the y-coordinate. So moving on, we are then going to, while not pq.is empty, we are going to use the starting position to traverse the rest of the nodes that we need to reach the end of our grid. So we're going to have an integer array called current, and that is going to be pq.pull. So whatever was at the top of our queue. And we're going to say, hey, integer obstacle is going to be equal to current of 0 as well as row is equal to current of 1 as well as column is going to be equal to current of 2. So this is why we stored our minimum or our priority queue like this. Current of 0 is going to be the either 0 or 1 value if it's an obstacle or not. Row or current of 1 is going to be the row value, and current of 2 is going to be the column value. So boom. Next, we are going to check if we've reached the bottom right corner. We're going to return our result. So if row is equal to m minus 1 and column is equal to n minus 1, we found our guy. So we're going to return our obstacle, and that's all we have to do. Otherwise, we're going to explore the 4 possible directions from our current cell: up, left, down, and right. And that's why we already made our previous integer grid direction. So for each integer array direction in directions, we are going to use each of these to traverse a new way. So int new row is going to be equal to row plus direction of 0, and our new column is going to be equal to column plus direction of 1. And it's going to go through each of our 4 directions, and we're going to check if is valid grid new row new column. So we're going to call to a helper function called isValid, which is simply going to check if the if our new row new column are within the bounds of our grid. If so, we can continue. Otherwise, it will skip this value. But let's say if it is valid, we are going to first create a new obstacle value. So int new obstacle is going to be equal to obstacle plus grid of new row of new column. So this is either going to be a 1 already, a 2 already, or a 0, and it's going to add whatever the new position is. So let's say if we're starting here, our value is currently 0, and then we're going to move here. Well, the value of this position, or grid of new row, new column, is 1. So it's going to be 0 plus 1. Our new value is 1. So, moving on from there, we are then going to update our path for our Dijkstra algorithm. Update our path if we found a path with fewer obstacles in a new cell. So if our new obstacle is less than the min obstacle of new row, new column, which remember everything was initiated to infinity, Then we are going to set our min obstacle of new row, new column, equal to this new obstacle value. Then we can add it to our priority key, which will allow us to traverse it in the future, or traverse its neighbors in the future. So that's it for our main function. Last thing we have to do is set up our helper function, or sorry, we're going to have to return. So we're going to return our min obstacles of n-1 and n-1. But that's it for our main function. We're now going to set up our helper function to ensure that we are within our grid constraints. So private boolean is valid, is going to receive an integer 2D array called grid. It's going to receive an integer row and an integer column, and we just have to make sure our column and row are within the grid. So we're going to return if our row is greater than or equal to 0, and our column is greater than or equal to 0, and our row is less than grid.length, and our column is less than grid of 0.length. So as long as all those conditions are met, it will return true. So if we run this, passes our test cases, and if we submit it, it passes all solutions. Thank you. Follow for more daily LeetCode solutions. If you're interested in learning how to code, check out the link in my bio for a resource roadmap in Discord and Patreon. Thank you.